So good morning, gentlemen. So to introduce the program today on connected and autonomous or automated vehicles with the acronym CAVs, I wanted to start with some background information. 12 United States now authorize the testing of autonomous vehicles, while 16 states and Washington, D.C. now authorize full deployment of CAVs. Of these, 18 states now allow testing or deployment without a human operator in the vehicle. The Institute of Transportation Engineers, or ITE, an organization I belong to, in their October, this month's issue of their ITE journal, their magazine, they noted these facts, and they added that this organization views this technology as a key way to achieve zero road fatalities and serious injuries by 2020. Now, if Mark will post the PDF that I had asked for, if you can post that to share it. Okay, so the February, by contrast, the cover text of the January 2020 Engineering News Record magazine stated, "Smart moves." Now you can't see that. It's hard to see the text, but I'll read it. As transportation stakeholders test intelligent infrastructure for connected and autonomous vehicles, uncertainty remains regarding the broad adoption of these emerging technologies. And the internal article in the magazine quoted one urban planner as describing the future of transportation as one that could go either way, a hell of autonomous vehicles mindlessly roaming the streets, causing ever more congestion, or a heavenly mobility network that is efficient and intermodal and contributes to sustainability, social justice, and safety. So our speakers today will provide an overview of the research they are conducting at NJIT, New Jersey Institute of Technology, on connected and autonomous vehicle technology, and help clear up the uncertainty expressed in the ENR article. So our speakers will start with Dr. Branislav Dimitrijevic. He is an assistant professor in the NJIT Department of Civil and Environmental Engineering. He has a PhD in transportation engineering from NJIT, and he specializes in transportation systems analysis and intelligent transportation systems, among other specialties. His research for New Jersey Department of Transportation has included development and implementation of regional computer simulation models for congestion and mobility analysis, road weather management, and traffic signal system prioritization. Dr. Joyoung Lee is an associate professor in the NJIT Department of Civil and Environmental Engineering. He has a BS in Transportation Engineering from Hanyang University in South Korea, and MS and PhD degrees from the University of Virginia. His research focuses on the development and evaluation of intelligent transportation system applications, covering connected and autonomous vehicle-based intersection controls. Dr. Lee has received numerous awards for his research activities, including the Best Paper Award on CAVs at the IEEE Vehicular Technology Society Conference in September of 2019. Now, IEEE is the Institute of Electrical and Electronics Engineers. Now, Dr. Lee has asked me to just confirm that he is a civil engineer. So with that, I'd like to introduce our speakers and have them take over and give us their presentation. So starting Dr. Dimitrijevic.
Thank you, Marv. So let me share my my screen. Let me just see where my PowerPoint is. It was there, but now I cannot see it. Huh, interesting. Okay, finally. So hopefully you can see this in full screen. Good morning, everyone. Marv, thank you for an introduction. I'm just gonna dive into our presentation right on to kind of avoid wasting time. and put more time into the topic. What I'm going to talk about, we're going to have two parts of the presentation. First part, I'm going to cover one of the recent endeavors that Dr. Lee and our team and myself have been working on in Newark, close to NJIT. And mostly I'll be focusing on that C part of CAV, connected part. And Dr. Lee will kind of then talk about that, plus some autonomous vehicle implications of what we've been doing. So my presentation is going to focus on what we call integrated connecting urban corridor in downtown Newark, nearby NJIT's campus. Just a little bit of background. We started kind of working on this idea back maybe 5 years ago when USDOT announced what they call Smart City Challenge. And there were numerous cities around the country that competed for a $50+ million prize or grant to develop smart city technologies and integrate them in their cities and city functions. Newark, City of Newark competed. We helped them develop some proposal with some ideas, focusing on transportation as a critical component of an urban system. And unfortunately, Newark didn't get a grant, but we've used this to as a springboard for some other ideas and projects and proposals that we pitched to New Jersey DOT and US DOT, and we thankfully received some grants to implement some of these things in Newark. Our work really focuses on these three vision elements that were formulated by USDOT when it comes to connected and autonomous vehicle technology. The three key components are infrastructure, data, and people, and kind of connecting them together in a seamless integrated system allows us to take advantage of new technologies, especially information technology, and implement these connected and autonomous features, both in terms of vehicles as well as travelers. Each one of these components has, let's call them subsystems or sub-elements. Infrastructure is based on intelligent sensor-based infrastructure components, various kinds of sensors, detectors that we integrate with our intersections and highways. Then also connected vehicles that actually interact with this infrastructure as they move through the network. Data is also a very important component. All of these sensors, they collect data. Connected vehicles also collect data, and then figuring out a way to integrate, to first of all exchange and integrate this data, and then use it to develop some analytics is and again very critical to developing applications of connecting autonomous vehicles in transportation. Of course, data sharing and coming up with standards and policies, ensuring that this data is seamlessly shared among different users, and that everyone is kind of using the same platform to communicate with each other. Otherwise, when we speak different languages, in terms of data, it's very hard to understand each other and exchange information in real time, especially. And then last but not least, people. People are really using all this transportation infrastructure and data, and they're making decisions about their travel. And it's very important to develop applications that will really focus on how people use transportation system and how they manage their travel and transportation decisions with input from the transportation system. All of this requires collaboration and partnering among multiple entities and stakeholders, and that sometimes is difficult, especially since there are different let's say, standards that are followed by different entities and different stakeholders. So that's again critical component in implementing these systems in real life. So going back to real life, what we try to do is do bits and pieces of this kind of in an integrated fashion and implement some connected and down the road, hopefully autonomous vehicle technologies in Newark. what you can see now is a map of downtown Newark, and the NJIT is located somewhere in the middle of the screen. I don't know if you can see my cursor, but it's around here. This is Newark. This is NJIT campus right here. This little piece here, Warren Street, is right in the middle, runs through the middle of the Newark campus. But the network that we try to integrate in this system integrates 13 intersections along Raymond Boulevard, which runs from Penn Station in downtown Newark all the way to NJIT. And then we have another piece of road infrastructure called Warren Street and First Street, which when you connect them, lead you to Interstate 280. So what we try to do is to kind of connect a transit hub through the network of streets in the downtown Newark to a major interstate highway. So our first part of the project is to instrument the intersections so that they can facilitate this connected vehicle technology and some kind of communication between vehicles and intersections as the vehicles travel through those intersections. Our total length of the test bed, as we call it, is about 1.7 miles. And what we did, we instrumented each one of these 13 intersections with some specific connected vehicle technologies, which I will introduce in a moment. Just for those of you who are not traffic engineers, just a quick kind of overview of what the intersection signal control includes. And you can see here a sketch that shows different components of intersection signal control, starting with what we can see when we get to intersection. We can see the signals, traffic signals. We can see pedestrian signals. Pedestrians know that in some intersections there are pedestrian push buttons where you can push the button and indicate to the intersection signal control system that you are there and you would like to cross the street. So you're asking for what we call right of way, to a green light to cross the street. There are also some detectors, cameras, loop detectors, different kinds of technologies that we can use to detect presence of vehicles at intersection. What that helps is determine when to turn the signal on, so to speak, and let the vehicles from a specific approach go through the intersection, and when to kind of stop and let the other approaches go through. All of this is really managed by signal controller, and you can see that in this cabinet, and usually every signalized intersection will have a cabinet nearby where all this kind of intersection brain is located. This is where you have all the components of the signal control technology or electronics that connects all these pieces of the system that you can see outside, signals, detectors, push buttons, everything like that, and then has some kind of logic built into it, some kind of computer that calculates, when to implement what kind of traffic plan or how to manage the signal timing to maximize the throughput or optimize the throughput of both vehicles and pedestrians through the intersection. So what we try to do is kind of add some intelligence to this system and add communication pieces that will allow this intersection to talk to vehicles that are approaching the intersection. And not only that, down the road, similar technology can be used to also talk to pedestrians and bicyclists who are approaching the intersection and would like to go through it, right, without stopping and safely. So what we added, first of all, we added what we call smart box, or some kind of little computer that can talk to the controller and can learn from the controller what the controller is up to. How much time is left on the green light right now, and when it's gonna turn red, and then what happens next. How long is next phase gonna last, and then send this information through some kind of wireless communication to the vehicles, right? So we use something called DSRC or short range, dedicated short range communication, roadside unit, which is a box that communicates with vehicles using some wireless technology, and transmits this data directly to the vehicles in real time. And you can see that the vehicles have to be also equipped with some kind of transmitter and receiver to be able to talk to this DSRC unit, and through that unit to the signal cabinet. Similar technology can be used, or 4G LTE technology can be used to also transmit this data to pedestrians, bicyclists, as well as other users who may not have DSRC communication in equipped vehicles. We also wanted to add, actually we are working right now on adding air quality sensors and weather sensors to the intersection. So that will add additional information to both the system users as well as to the signal control operators, to be able to kind of better manage signal control at the intersection using air quality and weather information. For example, minimizing number of stops and minimizing number of vehicles idling at the intersection would improve air quality. So if we can come up with these algorithms that will detect how many vehicles are there, how many of them are stopping, how long they're idling at the intersection waiting for the green light, we can minimize number of those vehicles. We can change signal timing to minimize number of vehicles that do this, and by doing that, we improve air quality. We reduce emissions, and we improve air quality. So that's another thing that we can do to kind of utilize some intelligence at the intersection to better manage traffic flow. One of the applications that I'm really going to focus on today that we've tested is what we call traffic signal advisory and eco driving. The kind of like a short of this is that as the vehicle approaches to the intersection, all of us, all of us drivers, we would like to go through the intersection without stopping, right? So we would like to go there and catch a green wave, so to speak, right? So go through the intersections without stopping. So what we are trying to do here, we are trying to establish communication between vehicles and intersection, where intersection will tell the vehicle how long this green light, or first of all, what kind of indication is on the traffic light, and then how long it's going to take. By knowing that, vehicle or the driver can adjust speed if there is enough time to go through the intersection without stopping, and that is going to also depend on speed limit. So, but if there is enough time driving at the most at speed limit, we could adjust the speed so that we can smoothly go through the intersection without stopping. The other way around is if we are in the condition where we would need to stop, at least we would get that indication on time so that the vehicle can safely stop before reaching the intersection, without really trying to go through it and then realize in the last moment that you can't do it, and then there are many unsafe conditions or situations that can arise. So the bottom line is we would like to be able to show to the driver the information about next traffic light, and depending on the position of vehicle and the position of the intersection, calculate what is the optimal speed of the vehicle to either go through the intersection without stopping, or inform the driver, hey, you can really make it through, slow down, and just safely and calmly come to the stop, and wait for the green light afterwards. So what we did, we developed a mobile app that is capable of utilizing this DSRC as well as 4G communication to communicate the information between the intersection and the driver. And it has several indications. Number one, it has the intersection name, the next intersection, signal status, which is currently what is the intersection showing, a the intersection showing, how long it's going to be, let's in this case green for another 15 seconds, and this is a counter that is kind of counting down the remaining distance to the intersection. And we have then advisory speed, and we give you a range, right? Usually it's a range between, in this case, let's say 20 and 50 miles per hour. Of course, limitation is going to be speed limit. So we would limit the maximum advisory speed to be less or equal to the speed limit. So what this does kind of helps the driver understand, you know, the optimal speed and what to expect when they reach the intersection. The first thing to do for us was to equip the signal control cabinets with this equipment that I showed earlier, where we had to find a way to connect this technology, this communication technology, and computers that would kind of talk to the controller with the controller. And in Newark, in our corridor, we have several different types of cabinets and several different types of signal controllers, and they look different. So we had to kind of go and do some scouting and reconnaissance and get a lot of information from our colleagues at the Newark Department of Traffic Engineering. And so that was kind of interesting. And the idea was really not to come up with a perfect scenario where, you know, we would have the best and latest controllers, most modern ones, but really work with what's out there. And many intersections in New Jersey, but also nationwide, do not have the latest and greatest technology. And it would be very expensive to replace all of that with, you know, brand new technology that's, you know, connected and autonomous vehicle ready. So we try to find a way to retrofit or to kind of use whatever is there in the cabinets and find a way to still be able to communicate with those controllers. And that kind of raised some challenges really for us. Number one, some controllers really don't speak the language that connected vehicles speak. So we had to find a way to bridge that gap, to kind of find some interpretation in between, to be able to communicate the data from the controller to this mobile app that we have in the vehicle. And the second thing is, in many intersections, all the cables that were already there fully occupy the conduits. You know, these are the pipes between the signal control cabinet and all the other equipment that's installed in, you know, the signal traffic lights, different kinds of detectors, push buttons, all of that. So all of that needs some kind of cabling to bring the power and communication. And in many places, these pipes that City of Newark used to draw these cables, they were full, packed. We couldn't draw any new cables for our equipment. So we had to figure out a way to bridge that. And of course, we were not allowed to dig ditches and put more new pipes underneath. So we came up with a different solution that you know, was kind of cheaper and feasible for the scope of our project. So the solutions. Number one, the solution for compatibility issue, we had to bring, instead of just putting our little computer here that we would put anyways, and connecting this computer directly to the controller and, you know, reading the data from the controller and transmitting this data to our RSU unit that communicates with vehicles, we had to put additional piece of equipment that would translate a signal from the controller that's not really compatible with the connected vehicle communication, with our DSRC communication, convert that into a different type of signal or different type of message, which is called MQTT, or message queuing telemetry transport. And then that even wasn't enough. We had to put that into our mini computer, convert that to another data communication protocol called SNMP, which is the protocol that our RSU can understand, and use this whole system to transmit something called SPAT, signal, phase, and timing message between the controller and the roadside unit radio that communicates this data to connected vehicles. What SPAT means, signal, phase, and timing data, is essentially what I was showing you earlier. You know, what is the current phase that the signal controller is showing on traffic lights? You know, which approach has green, which approach has red. How long is this phase going to last? For another, I don't know, 10, 15 seconds. It's counting down, and then tells you, what the next phase is going to be and how long that phase is going to last. So once we know that information, we can, kind of transmit this information to the drivers, to the vehicles approaching the intersection. So kind of, again, we had to come up with a scenario or a solution that would allow us to convert certain data, to translate certain data to a language or format that can be understood by the off-the-shelf DSRC connected vehicle technology. The second issue with conduits we resolved by, instead of digging ditches, using wireless communication. And what we've done, we've established a point-to-point Wi-Fi communication between the controller cabinet and our RSU. So you can see that conventionally we would have a cable going from the cabinet into the pole and then through the pole to our RSU. Instead of doing that, because we didn't have room in these conduits, we installed a Wi-Fi access point and established wireless communication. So instead of using a wire, we were kind of communicating back and forth using wireless communication. So that kind of saved us a lot of money and time, but it comes with some delay in data transmission. So this is how the intersections look like after we installed everything. You can see the cabinet. We added a little bit of equipment here. This is that translator kind of piece. This is mini computer that we use to get the data that's translated by this translator and then convert that into a signal that can be transmitted through our connected vehicle DSRC radios. And the radios are kind of shown here. You can see one of our crew members installing the DSRC RSU unit and the radio. So the Wi-Fi radio. So you can see here, this is DSRC communication radio, which communicates with vehicles, and this is the Wi-Fi access point. That's the piece of equipment that actually communicates wirelessly with the signal controller. So that's the roadside piece. So that's the piece where we equip the intersections. In order to communicate with intersections, we also have to have some equipment in our vehicles that's capable of establishing this communication. So what I'm showing you here is one of the NJIT vehicles that we are turning into an autonomous vehicle, and it has lot of different technology on it. So one by one, first you can see it has all kinds of antennas which allow us to kind of establish communication with roadside infrastructure. So we have DSRC antenna, which is used to communicate with the roadside DSRC unit that I was showing you earlier. We have 4G LTE antenna, which allows us to communicate using 4G LTE cellular communication. Down the road, that would be replaced by 5G. And we have GPS GNSS antenna, which allows us to actually have a very precise location of the vehicle in real time. And that's very important because, as you saw, we need to know where the vehicle is in order to calculate the distance from the intersection and then calculate all the other telematics information. So that's the antennas. The next thing is there are some detectors on the vehicle. I'm not showing you radars. Our vehicle has some radars that are built into the bumpers and the doors, but we also have a LiDAR. And LiDAR is a piece of equipment that kind of is detecting objects and the distance between the vehicle and objects surrounding the vehicle. What that does helps us, as you can see, visualize all the objects that are surrounding the vehicle as the vehicle is moving. And you can see on the bottom here that we can kind of then use this information to make adjustments in speed and position of the vehicle in order to avoid these objects or obstacles. And these objects could be other vehicles, it could be curbs, it could be pedestrians, could be many different things. And then we have camera. Okay, let me just go back. So we have DSRC onboard unit. So mentioned that we need to be able to communicate with those DSRC radios at the intersection. And this is the unit that is connected to the antenna. and this is where the data from the SRC is processed, and then it's sent to our mobile app, which I was showing you earlier, will show us, the signal at the next intersection, how long it's gonna, last, and it's also going to tell us the optimal speed the vehicle should be traveling. Lastly, we have camera, and this camera is used also for object detection. It's used for also down the road some kind of other connected, actually connected autonomous vehicle technologies, where we are going to be able to, again, calculate the distance from the vehicles in front, or calculate the distance from other objects such as pedestrians, make adjustments to speed, or when it comes to autonomous driving, directly inform the computer and the drivetrain about whether the vehicle should brake, or whether the vehicle should reduce speed, or stop, or just continue driving at a trajectory that was established by the drivetrain or by the computer. So all of these pieces of equipment are integrated in one kind of system within the vehicle that allows the vehicle to communicate with the infrastructure directly or indirectly, let's say through 4G or 5G communication. This is a display of our intersection traffic signal assistance system mobile app, and you can see that it has several pieces of information there, except apart from traffic signal countdown and advisory speed and position of the next intersection. We are also calculating fuel consumption and air emissions, and we can use this information, fuel and emissions, to make adjustments in vehicle motion in order to minimize fuel consumption and minimize emissions. This is what US DOT is calling eco driving, where we can utilize some modeling to inform the driver about optimal driving behavior to minimize the consumption of fuel and minimize emissions of the vehicle as it moves through the network. This is a short video of how this works. This is taken at in the corridor at NJIT. So you can see now, you can watch in the bottom, this is the display in our vehicle, and you can kind of see how it changes as the traffic signals change as well. So you can see now we are approaching another intersection, and we are counting down you can't see it here, but it's kind of counting down the time remaining at the green light. And then as soon as we pass the intersection, the vehicle will pick up communication from the next intersection and will start counting down again, depending on what that intersection signal is showing. And then this would kind of repeat as we go through the corridor. It also knows the speed limit and will kind of make adjustments in the advisory speed based on the distance from the intersection and with consideration of the speed limit at that intersection. The video is also available on YouTube. I just have it there just in case of any issue with the video streaming. So the current status of the project is we have 13 intersections in operation. We are working now on adding air quality sensors at 3 intersections within the corridor that will help us start testing with air quality analytics as well within the corridor. We've been successful in broadcasting SPAD, signal phase and timing messages from all 13 intersections, as well as map messages. Map messages are really is information about the intersection design, number of lanes, lane widths, their position, and so forth, so that vehicle approaching the intersection knows what kind of roadway geometry exists at the intersection. So that will help kind of make adjustments in trajectory if needed, as well as understanding how best to go through the intersection. Besides that, we also successfully broadcasted what is called basic safety messages from the vehicle to the intersection. This can be used down the road to inform the signal controller to take some actions to ensure safe operation of the intersection, considering the behavior of vehicles approaching the intersection. Of course, all the vehicles, or many of them, will have to be equipped with the appropriate technology to be able to communicate these basic safety messages to the intersection. We also evaluated communication, as I mentioned, introducing that wireless communication between the controllers and the DSRC units does add to some latency, so that may impact some of the applications down the road. We have some plans to add more applications to these intersections, and that will also employ some of the technology that is already there. We'll need to also develop some intelligence within our vehicles to be able to take advantage of this information and introduce something called cooperative intersection collision avoidance, which is a safety application, and also introduce pedestrian signal and pedestrian crossing applications, which will actually allow pedestrians to take advantage of this communication and be able to both understand what's coming, what kind of signal timing exists for pedestrians, but also tell the intersection without pushing the push buttons that, they are there and they'd like to cross the street. We also are looking next year at trialing 5G technology in this corridor. We have some plans to work with AT&T to introduce 5G communication in the corridor as well. Another application, and I don't know how much time I have, probably not much, is our weather data, and that is another piece of equipment that we put on our vehicles, where we collect data from the roadway about roadway condition, as well as air temperature, air humidity, and we can use this information to inform the traffic operators as well as other drivers of the roadway conditions. And that information then in turn can be used to make adjustments in driver behavior to ensure safe driving, as well as to ensure mobility on the roadways, especially during adverse weather conditions. So again, all pieces of equipment have to be kind of installed. This is again one of the NJIT vehicles. You can see road weather sensor at the back of the vehicle, some communication devices in the trunk. This includes routers, camera processing unit, things like that. And then also you have some system control that exists in the cab, where we use some computing equipment to number one, collect the data from the sensors, transmit this data to the our database or central server, and then get some analytics out of that data and show it to the driver in real time. And this is how it looks like through the web user interface that we developed, where we are showing this information as it becomes available from the vehicles. We can now develop different kinds of mapping, showing to the operators where we have ice, where we have snow, where we have wet surface, and that can help us determine maybe some kind of messages that we can show to the drivers, and messages that we can show in terms of reducing the speed or alerting the drivers of unsafe or adverse weather conditions ahead. In all of this, in order to avoid any accidents or some kind of unsafe driving behavior of drivers that maybe do not expect or cannot detect in real time the adverse conditions ahead of them. Some other things that we are trying to do is use this information to provide awareness to traffic operators. And so you can see that, if you have a bunch of readings in real time, you can see you can develop some applications where you can kind of show that for the entire roadway network. That's my piece of the presentation. I'll stop sharing at this point, and Dr. Lee is going to pick up next. I don't know if you wish to entertain questions now or later?
I would suggest that you hold questions, because if we start going into discussion now, we won't leave enough time for Joe.
Sounds good.
Okay, can I just stop? I start.
Go ahead, Joe.
All right. Sorry. Well, before getting into the presentation, I have to say this. It is my great honor to grab a chance to present our research activities at the Old Guard meeting. I know we're supposed to have some sort of the Q&A session at the end of the presentation, but I have to respond to two quick questions from the audience during the Dr. Dimitrijevich's presentations. One about the LiDAR. The question was about whether the LiDAR will be broken in the car wash. Maybe we don't know, but that is the exactly same reason why I never get into the car wash the facility before. And then the gentleman had a question about the video recording. Branislav showed. He said it is recorded at 3 a.m. But as far as I properly remember, it was recorded around 8 p.m. sometime in February or something. We had to make some sort of a condition to get a certain kind of some kind of conditions that we can replicate the concept we developed in the real world. That's why we selected that time period. So here, what Branislav presented so far is about the actual deployment of this new technology to the real world. As a transportation engineer, one of our primary job is to examine the effectiveness or impact of new technology when it is spread out to the real world in the near future. As a part of those activities, one way that we can do is to make a certain dedicated test bed in the real world, and then get some idea about the feasibility and then availability of this technology to the real world. But the thing is, with this real world test bed, the scope of getting that examinations or evaluation of performance are often very limited, because the number of actual devices that we can deploy are not kind of the unlimited. So we have to stick to a certain the locations and the corridors, and the user of those the new technology are not fully ready to check each actual broad impact in the real world yet. So, but still, we need to know what will happen with that. So another way that we can take is to use simulation. So what I'm going to present as part of the Dr. Dimitrijevich's presentation is the broad impact of this new technology we called in-vehicle traffic signal assistance system under different conditions, like different congestion conditions or different number of users. We call it market penetration rate, or even some kind of different kind of strategic the policies to implement this kind of technology with some risk-free condition, and by the achieving time and effort saving under simulation studies. So we then came up with two traffic congestion conditions for the simulation of this ITS impact analysis. One is moderate traffic, and the other one is heavy traffic, which sound very the vague at this moment. But if I give you guys some sort of the heads up about the meaning of moderate and heavy traffics, the moderate traffic is like that when you get into intersection, you see about the 3 or 4 vehicles ahead of you. So, well, maybe you can just pass the intersection, go through the intersection without any significant some sort of the delay or waiting time at the intersection. But the heavy traffic, when you arrive intersection, you see a lot of vehicle ahead of you, maybe 10 or 20 or in between. So, well, in many cases, you can pass the intersection at the end of the green time, but sometimes you cannot go through the intersections, which result in what we call cycle failure. That kind of condition is, I would like to define as heavy traffic. Also, we came up with several different scenarios of how many users are available on the roadway, starting from 0%, meaning no one's are able to access this kind of new technology, and the 100% perfect market penetration rate, because everyone has this the equipment to communicate with this new infrastructure, which is completely ideal of a ceiling condition. And we also developed a certain plausible strategy to increase the use of this new technology by adding a certain dedicated lane to see whether this strategic approach can kind of the speed up the deployment of this technology to the real world. With this, the scenarios, we developed it, simulation models, and then checked how this technology will affect our world with respect to the mobility of intersections control. Before getting into there, I would like to talk about a certain enhancement to these existing ITSAS applications to deal with some available feature of automated vehicle. What Dr. Branislav Dimitrijevic mentioned is about some sort of connected vehicle piece, actually. But we can utilize some automated vehicle capability by having vehicle itself to control its speed based on, based on advisory speed coming from the intersection control system. Here we developed an algorithm we called trajectory-driven optimization for automated driving, or TOD, which makes individual equipped vehicle can adopt existing signal control system so that it can pass through the intersection within, we call green band, like that. Here, I don't know whether you can see my cursor here, but up here is about the normal conventional driving behavior on a signalized intersections corridor. If drivers arrive at intersection in the red, then they have to wait here and until the green comes up. But with this automated vehicle feature coupled with communications from the intersection controller, vehicles can adjust their speed to go through the intersection when green comes up. So, well, it includes a lot of long story, but we developed this kind of algorithm and then tested in the simulations as well. But maybe the question would come from audience about what happened to the vehicles that already arrive at the intersections that could not provide any information about their delay or waiting time, which might block the vehicle's movement on here with the green time without with this kind of the weighted vehicle. So we also developed another algorithm to predict that kind of the delay time of traffics for a certain the approaching street by using the machine learning techniques. So with that, then we applied those two algorithms into ITSAS application and then tested it on simulation environment, mimicking two real-world roadway condition, one in the US Highway 1 in and around the Princeton area, which is about 5 mile long with 6 lane for both directions. And then the other one is also located on US Highway 1, but in Woodbridge, New Jersey, which has about the 5 miles, but it also has the same 6 lanes for both directions. Well, both the test bed corridor has about 55 mile per hour of the speed limit. So it actually carries over the significant amount of traffic daily. So with that, then we made a certain computer program to come up with the simulation test, and then collected some measures to examine its impact on the roadway. The one other measure that we collected, we called average stop delay, which is a major indicator to say the performance of intersection, which is called level of service of intersection. Well, and then we evaluated this, the applications with two different congestion level, heavy traffics and moderate traffics, with different market penetration rates starting from 0% and up with 100%. So obviously, with the increase of market penetration rate, we expect more benefits or more delay reductions are expected. So here, starting from 0% market penetration rate for this Princeton area, it's actually started from about 37 for heavy traffic, 25 for moderate traffic, seconds at the stop delay. And then as the market penetration rate increase, it could save the dramatic kind of the delay reductions, especially for moderate traffic conditions, which started from 25 per second to 5 seconds. So maybe 25 seconds, you expect about 5 or 6 vehicles ahead of you, but the 5 seconds of the traffic stop delay, maybe 1 or maximum 2 seconds, two vehicles ahead of you when you approach the intersection. But the heavy traffic condition case, maybe that the amount of the savings or the reductions of delay is not that great as much as moderate traffic, but still it could achieve such a the significant such a kind of the reductions as well, starting from 37 to the with the 0% market penetration rate, and then 100 about the 25 seconds with the 100% market penetration rate, but it actually kept showing the delay reduction as the market penetration rate increased for both heavy traffic and then the moderate traffic as well. And the same things or similar trend actually observed on another the test bed here, starting from 35 to about the 23, and then 25 to about the 7th or something for moderate and then heavy traffic respectively. We also measured how many vehicles are able to be processed or solved with this different the technology market penetration rate here. For heavy traffic case, it would make some sort of the marginal. For the moderate traffic case, well, the number of vehicles solved are not that much great different. But the heavy traffic congestion case, this new technology is expected to improve a slightly increased number of vehicles served for both the simulation case here. Well, we also we investigated overall the corridor-wise the performance by using the average travel time measure. I have to mention that the stop delay is all about just an intersection, but the travel time measure is a good indicator to see the impact of a new technology on the entire corridor. So here, the similar patterns we observed from the delay are also discovered as shown on this chart for both heavy and then moderate traffic conditions respectively, and especially moderate traffic conditions made a kind of very significant the amount of travel time reductions with the 100% market penetration rate, which might not be realized in the near future. But even some lower market penetration rate, like a 20% or the 30% within, I don't know when, but maybe next 10 years, with this new technology, as long as we are able to connect the vehicle and the infrastructure communicate each other, then we can have about 2.7% and 2.1% of travel time reductions for both heavy and the moderate traffic congestion condition respectively. The similar the observation also discovered from the other test bed with also 3%, 30% of market penetration rate, it could make some sort of marginal or acceptable the travel time reductions can be obtained from the simulation result. I mentioned one of the strategy to increase the use of this new technology by applying the dedicated lane concept for automated vehicle. Well, that is another might be a good kind of the push to have more people to participate in the adaptation of new technology in the short time period. But well, having that kind of capability of their cars actually requires extra payment to buy those equipment, and then taking the services need some money, extra money to get into. So if we conduct these dedicated lane strategies, then the people who are able to afford those new technology and equipment will be able to get the benefit, but that would result in a certain some sort of the equity issue by those who are not able to afford those new technologies. To investigate what is the impact of these new technologies to two different groups of people, we also applied the simulation model and then looked into what happened to two different groups of people with this dedicated lane strategy here. This chart shows that under moderate traffic congestion conditions, up to say 20% of market penetration rate here, as you can see, this orange the line indicate the no equipped vehicle, and then blue is the equipped vehicle. Well, up to 20% of market penetration rate, the travel time saving for both groups are almost identical. It's about 2.3% or 2.0% travel time saving, meaning that without this the equipment, well, up to 20% of market penetration rate, both group of people can save their time. It's like the win-win things. Well, overall, not just only 20% of market penetration rate, well, even higher market penetration rate, as you can see here, both groups of drivers actually make some savings of travel time under this connected and automated vehicle environment. But starting from 30%, the travel time savings for equipped drivers are a little bit higher than unequipped driver here. But still, it shows that both are able to make some travel time savings as well. Well, same thing happened to the other simulation test bed as well, with a similar consistency to the Princeton test bed with the 20% market penetration rate. Their travel time savings are not that much different, but after 30, well, it goes up to a certain the differences up to the other 10% and 60% of the travel time savings as well. But with more than 80 or 90% of market penetration rate, then both groups are able to maintain the similar travel time savings. Well, I would say then depending on the market penetration rate, their travel time savings might be different, but they could have at least the positive travel time savings as a benefit of doing these new technologies. Well, but the under heavy traffic congestion condition, well, first of all, the travel time saving difference are not that much great different. With equipped vehicles, with the 20% or 30% imperfect market penetration rate, observed to reduce not the travel time of not just only equipped vehicle drivers, but also unequipped vehicle drivers as well. Same, the patterns also discovered on the other the simulation test bed as well, as you can see. So, well, I would come up with a conclusion with respect to this the simulation result that this new technology, as the magazines said, we don't know whether it will go to the hell or the heaven, but at least it can make some sort of positive benefit for both the drivers who are able to get the devices, but also the drivers who cannot make these devices in the near future as well. And then, so this is the similar but the different types of chart to show how the two different vehicles drivers are obtaining the benefits as well. The similar patterns are also observed from the moderate traffic case and then heavy traffic as well. Well, I don't know how much time I have, but let me briefly summarize what we found from the simulation. Well, we maybe conclude that with 20% of market penetration rate or less, there are several some kind of the benefits, but the benefits are very marginal from the reserved lane. So maybe before getting into the 20 or 30% of market penetration rate, it would not be a good idea to take that the dedicated lane the strategy. But under moderate traffic conditions, the market penetration rate are higher than 20% actually made about the 2.5 to 19% of the travel time savings, which is a huge the benefits and then sizable. And then but the heavy traffic congestion condition or the travel time reductions, it's more significant than the moderate traffics, making the 5% to the 9%, depending on the market penetration rate. But it actually made more the significant travel time saving on the low market penetration rate. And then, well, in case of the market penetration rate lower than 60% with the heavy traffic congestion condition, well, that is not that much great kind of the difference with and without the dedicated lane strategy. So, well, then with these simulations, we were able to examine that technology, or we call ITSAS, in vehicle traffic signal assistance system, is also some sort of the application that we can think of as a part of this new technology deployment that can come up with a broad impact to not just only the equipped drivers, but also unequipped drivers as well. And then it could be a good kind of alternative for us to make some sort of this kind of the quick deployment of this new device by applying dedicated lane strategy. All right, this is pretty much of my presentation, and then I've seen there are several questions from the audience, but I think me and Dr. Branislav can answer for the questions. Thank you.
Okay, we have some hands raised, and I'd like to call on Al Aho first. I'm asking him to unmute himself.
Hi, I'm Al Aho, and I'd like to thank both speakers for a very interesting project and a highly, highly challenging project. I'm very interested in, for ITSAS, do you have a quality plan? All engineering systems require a quality plan from where I come from, having worked at Bell Labs for many years. And I was particularly interested in how do you ensure the quality ensure the safety of people and property in your system? What kind of provisions have you put into your system to make sure that happens? Your system depends on software as well as hardware. And as you're well aware, in the medical area, there are very stringent requirements for what kind of software can be used when you're dealing with human subjects. The other aspect is, since this is an automated or connected to the internet, what provisions have you made to make sure that hackers can't get in and compromise the system? So there are many, many dimensions to quality, but I'd be very interested in what your thinking has been on both safety and security for ITSAS.
Dr. Dimitrijevic, you want to start first, or?
Yeah, let me start and then you can kind of add to it. So, well, thank you. Excellent question. Obviously, it kind of goes perhaps a step beyond the scope of what we've done. So just to kind of clarify, this is a research project, so it's not a commercial project where we look to actually put this in hands of users and anyone, you know, be able to download this app or use it in their vehicles. Not to say that it's not possible to do so. In fact, there are some applications out there that developers, including some aligned with Google, are developing and integrating into vehicles such as BMW or you know, Audi. I know they have these applications integrated in their newer vehicles. The first aspect of safety, so these are all advisory messages that are being displayed. It means that still driver makes the decision, right? So it's important to understand that the more information one gets through the vehicle interface, the more or the less a driver can be focused on the roadway, right? So it's kind of this information overload where you don't want to distract the driver too much. So positioning of this display is important. Perhaps using a cell phone is not the best way to do it. So, you know, in the driver dashboard is probably better to display this messaging. We haven't done this together with the vehicle manufacturer because it's just part of our ongoing research. So we've used the mobile devices that we were placing in front of the driver to get this information seamlessly and without too much distraction. As I mentioned, the communication issue is something that we've been looking at. Some of this information needs to be delivered in real time. And if you have delay between the information being delivered to the driver and the information when the information was created, that can cause obviously discrepancy, and the driver reaction is going to be too late, right? After the actual information is being created. For safety critical messages, we are talking about some limitations in terms of milliseconds. The information that we deliver, such as signal timing, remaining green, anything below 1 second delay is still acceptable, meaning that communication delays below 1 second, let's say 500, 600, even 700 milliseconds, is still going to allow the driver to react appropriately, adjust the speed, or reduce the speed and come to a full stop in timely fashion. And the third, I think the most significant issue is that we are not considering in our application presence of other vehicles on the road. So our ITSAS application only calculates the distance between the vehicle and the intersection and the optimal speed as if there is no one in front of you, right? So essentially you have open street and you can go or not go depending on just what the signal is showing. In reality, you may have vehicles that may be in front of you that prevent you from achieving that optimal speed. So that's something to consider in the future. To be able to do that, we need to have higher number of vehicles participating in this network and this communication. What Dr. Lee was saying, market penetration is very important, because the more vehicles are equipped with this kind of equipment and these devices, they will be able to communicate with intersection and with each other. And so therefore, we'll be able to make adjustments considering presence of other vehicles that can be detected in the system. As far as security, I'll let Dr. Lee talk about that. We have not directly considered this, but that's really something that we that was supposed to be, or is supposed to be taken care of in this off-the-shelf equipment that we used. So we didn't develop these protocols. We didn't develop these roadside communication units. This is all developed by companies that are following IEEE and SAE guidelines and specifications for connected vehicle technology that include security and protection of both privacy and access to this data. But Dr. Lee, maybe you can add a little bit more.
Okay.
Let me just jump in to give some more about the security issue of this system. Well, while the protocol itself has been developed to consider more enhanced security protection for the communication of the system, but still that security part is the weakest part of this entire system architecture, actually. But there's no some sort of the significant the serious research activities or even practical the analysis regarding the security issue of this system yet, because just simply I believe not many people are actually using it yet. But well, in the society of not just only transportation, but also electrical and the communications engineering side actually started to look into any the vulnerable point of this the security part of this system as well. And then it's like ongoing. So maybe we can have some idea of a couple of years later, then can be reflected into this, not just only ITSAS application, but also any other connected and automated vehicle application as part of quality plan.
Bill Tittle, and question for you, Bill. Can we go on a few more minutes?
Well, it's up to our audience. Yeah, I think, I mean, and our guests, of course. I think that's okay. A wonderful presentation, gentlemen, and a really fascinating issue. You have to recognize your audience here is very anxious about implementation of this. For me, it's my great hope about being mobile when I'm 100 years old, if I make it to that. So what is the buzz about time for implementation of any whatsoever?
I can maybe again start first. So there was one comment from one of the colleagues from the audience about the recent deployment of Waymo vehicles in Phoenix. These vehicles have been in testing for several years, and they don't really have any communication with the system, the road infrastructure, right? It's really a vehicle as a bunch of sensors integrated together, trying to replicate the behavior of the driver, meaning see everything the driver sees, feel everything the driver feels, and navigate the vehicle through the network. So there is really no vehicle to infrastructure communication component there. I don't think there is also vehicle to vehicle. It's essentially only one vehicle has its brain, so to speak, that has been trained over several years of driving through that same neighborhood over and over and over and collecting tons of data. So it takes a lot of time to train a system like that to operate in a more or less small area. And now imagine if you want to now create this kind of system where you can buy this vehicle and put it anywhere in the world on any street, and it should work, right? It should just be able to go around without the driver. So it's not really easy to do that. It requires a very sophisticated mapping and learning about the specific area where the vehicle is going to operate. It needs to be able to recognize other vehicles, objects, pedestrians, animals on the road, anything that kind of would impede or otherwise affect the operation of the vehicle. What we focused on is not really driverless or automated driving. It's really this communication ability to enhance the vehicles sensing the environment around them by communicating information from the intersection or from the any roadway infrastructure. Waymo vehicles, for example, and other autonomous vehicles, they don't really know what the intersection signal is doing, and they don't care. Essentially, they have cameras that are watching the signal, and like people, whatever signal shows, the vehicle will react. What we are trying to do is enhance this by saying, well, if we can communicate to the vehicle what the infrastructure is going to do, then the vehicle has additional information that can be used to optimize the behavior or driving of that vehicle and other vehicles in the traffic stream. The more vehicles can communicate with the infrastructure and among themselves, the more optimized system can be creating. What we call in transportation planning system optimal, meaning we optimize the entire system by providing information to individual participants about how they should behave in order to minimize emissions, to maximize throughput, to minimize travel time for everyone. So in terms of when this is going to be implemented, as I said, Waymo is already implementing driverless in Phoenix, in a little area. So very, very kind of encouraging. It's a big step. The technology that Dr. Lee and I presented, is there. I mean, we've tested it. It exists. It's not only in Newark. It exists in many cities around United States, where different universities are trying different things. But it really comes down to be enabling this technology in vehicles, and working with car manufacturers, vehicle manufacturers, to embrace this technology and communication with infrastructure. One challenge is that they want to know that Newark is doing the same thing that Atlanta is doing, that Phoenix is doing, because they're going to be selling their vehicles everywhere, not only in one area. And these vehicles have to be able to communicate with all the intersections anywhere they go. So perhaps the issue is not just kind of establishing direct communication between infrastructure and vehicles, but using some kind of central system that can kind of communicate to all the vehicles in real time. And that's where 5G comes in. Right now, there is a lot of communication latency using 4G and LTE, but with 5G, that latency may be reduced tremendously. And we would be able to communicate this data using cellular communication to vehicles over long distances without much delay. And I think that's going to be the next big step, where 5G is going to probably be a game changer in terms of providing this technology inside the vehicles and connecting the vehicles with infrastructure. Dr. Lee?
Oh, that's okay. So we covered everything.
Mark?
Marv, would you like to come in, and are we at the end, or can we continue with questions?
Well, if there are any other questions, and if we have the time.
We have 3 more people with hands raised.
Okay.
Boppy, you're next. Please make it brief because we are running out of time.
I think it's a very good presentation. I just wanted to point out that there is a choice, a human element of it, and the other things like what kind of regulatory and things like that seems to be the more of a blockage about this kind of car and this kind of operation. Can you see that, whether you consider the human interaction part of it?
Dr. Lee, maybe you take this one first.
Well, yeah. So you sort of raising an issue between actual human drivers and then some sort of the machine drivers, and each some sort of the collaborations, and then each kind of potential regulations when it actually deployed to the real world. Is that the question?
Yeah.
Okay. Well, the Brian's lab, maybe you can jump in with my limited information, but there are some kind of the effort to make some sort of the policies for the operation of these new types of the vehicle driving, not just only the interactions between human and the machine, but also the actual operation of machine driving, because the majority of this new technology heavily depends on some sort of the vision computer vision technology using the camera. But the camera, unlike the human, cannot be precisely as much as the human driver's eye. So it often produces completely wrong sort of a decision based on completely misunderstood recognition or the perception of a certain object on the road. So to prevent that kind of some sort of the mistake from the machine vehicle, some relevant agencies like US DOT and then Federal Highway Administration Safety Board is coming up with some sort of the regulations, not just only for human drivers, but also infrastructure side. Let me share the screen, the snapshots that I got recently from different the presentation. Here is a case of automated drive cars crash. The one is this one here. The automated vehicle actually accepted this as the traffic signal light while they are driving, which is not actually the traffic signal light. It's the traffic cones tipped on the pavement. Well, with that kind of cases, well, we need to come up with a certain, not just the legal regulations, but also any requirement for the operation of the machine vehicle, but also the maintenance of the infrastructure and roadway as well. But it has not been fully developed yet, except for just some private side, like liability issues coming from the insurance and then the automated vehicle providers or something, but this kind of side has not been fully done yet, as I know.
I think, Mark?
Ron Weinger has a question. Ron, are you able to unmute yourself? You're just on the phone.
Guess not.
I have a question.
Paul had something to say too.
Yeah, this really connects with a number of the questions that have been asked so far. It's sort of a higher level question. I believe you're probably doing a lot of this work on government contracts, DOT contracts, and so on. And you tell me if I'm wrong, but I think that there are groups all around the country working on small pieces of the overall problem of creating intelligent infrastructures. And everybody, is working on their piece. Maybe there's some competition. There's a lot of cooperation. And ultimately, there will be standard setting bodies and government agencies that will be reviewing this. And there will be best practices emerging from all of this. The experiments that you're doing are essential input to making those decisions, but you're not making those decisions. You're working on a piece of the much bigger and more complex thing. So what's the bigger picture of how this will evolve and how soon these things will start appearing? And you got to make this quick because it's a big question, and I'm not getting you. There isn't time to give a full answer. I'm sorry.
Maybe I can start first, and then Bana, you jump in. My short answer depends on where. Okay, depends on where. Like a Phoenix, which has a lovely environment for not just only transportation infrastructure, but also weather. Probably it could be done within a couple, maybe 5 years or 10 years. For example, Phoenix, there's no such a severe weather like a rain yesterday, today, here in the Newark, New Jersey. And then there, the transportation infrastructure, like a condition of pavement, is really, really nice compared to here, right? That's why the Waymo guys picked up Phoenix, and before they come to the Phoenix, they picked up Nevada, some place to conduct this kind of pilot study as well. Yesterday, I played with my test vehicle to have my camera detect lane on the pavement, but the weather, as you remember, is completely wrong. So my camera cannot detect the lane at all, right? So maybe we here, people living in this New England or the East Coast area with such a severe weather and then not sufficient the budget for the infrastructure of transportation system may take a little bit more time than the other states in the West Coast or something, like California. I don't know whether this is the answer for your question, but
it certainly is a part of the answer. Yes, thanks.
Yeah, we are being urged to wrap this up. So I think at this point, Mark, if you can display our certificates of appreciation, I want to thank both of our speakers and let you know we have two ways of thanking our speakers. First, our certificates of appreciation, which are posted on the screen. They are the image of an orchid And this is because Summit was the orchid capital of the East, and when Old Guard was founded in 1930. And so we will send these via email to each of you. When we had our meetings in person, we would give them to you individually. Things have changed, of course. And our second way of thanking you is our Old Guard salute with a big round of applause. So thank you. Nice, an amazing presentation.
Thank you, Marv, and thank you, gentlemen. Wonderful presentation.